Hi. So I'd like to introduce you to the idea of a confidence interval. What we have here are two parameters that we know about a population. So let's pretend we know that the mean of a particular population is equal to 633.37 and that the standard deviation of that population is equal to 94.89. Now, for the time being, we're going to pretend that this mean represents the mean SAT score for a particular high school somewhere. Or I should say mean math SAT score, and then standard deviation here is the standard deviation of the population of all the math SAT scores in that school. All right, so we've talked about sampling distributions, and we know what sampling distributions are. What we can do is designate a sample size. So let's pretend we're going to take SRSs, simple random samples, of size n equals 30 out of this population, and then every time we pull 30 scores out, we're going to create an X bar. So there'd be a first X bar, and a second X bar, and a third X bar. And as a matter of fact, there'd be many, many X bars. And the list of all those X bars together is referred to as the sampling distribution for X bar. Okay. Now, we have an additional luxury here. The fact that n is 30, that's a pretty big sample size. We have something called the central limit theorem, CLT I'll abbreviate. The central limit theorem says that if n is large enough, and usually the guideline is 30 or greater, then that implies the distribution of X bar is approximately normal with a mean equal to the mean of the population. So mu of X bar, the mean of all those little samples, if we put all those samples and found the mean of all those samples would be the same as the mean of the population. And a standard deviation that's equal to the standard deviation of the population divided by the rad of the sample size. That's sometimes referred to as sigma of X bar. So in our specific example, what we can say is X bar is normally distributed with a mean of 633.37. I'm getting that from right here. And then keep a note of that number, 94.89. A standard deviation of 94.89 divided by the square root of 30. Okay, which, by the way, is this, 633.37, comma, and that turns out to be about 17.32. All righty, so let's take a look at this distribution for a minute and talk about this. So what we know is we have a normal distribution. The mean of this distribution, the mu of X bar, is 633.37, and the standard deviation of X bar is 17.32. Now, as a researcher, if your job was to sort of interview 30 kids and ask them what their SAT score was and compute an X bar, every time you did that, you would get another X bar. So, for example, let's open our calculator here. Bear with me for a minute while it opens. And while it opens in this calculator, I've put the results from a few different X bars that were calculated. So we're going to stat edit here. When we look at this first list, you'll see the first number there is 643.3. And then the number after that is 627.3. So what those represent are two different X bars that two different people calculated when they went and interviewed 30 kids and asked them what their SAT score was. And they pulled them from this population that we've been discussing, which has a true mean of 633.7 and a standard deviation of 94.89. Remember, when we look at the sampling distribution, the standard deviation got smaller because we had 94.89 divided by the square root of 30. So let's think about that. There was that 643 number over here. Somebody got a 643.3. And if we look back at our calculator, we had a 627.3. So that's over here, 627.3. And there's a whole bunch of them. Somewhere down here, there's a 609.67 if you look down on that list. So that's sort of interesting because that's a little bit far away. So a 609, which is over here somewhere. Okay. And what we have is a bunch of different X bars we can get. Well, in practice, most of the time, you don't know the true population mean. Usually mu of X is equal to some kind of unknown. But what you hope for is that these x bars that you calculate do a good job of estimating the true mean. So here's where a confidence interval comes in. What we can do is we can take our x bar and add to it and subtract from it something called an ME, a margin of error. And what that means is to say, we're pretty sure our x bar is a good estimator for the true mean, but we know that there's going to be some variability. We can see that in these three examples. Here's an x bar 1, an x bar 2, and an x bar 3. So maybe if we do plus or minus something, we can create an interval and say, hey, we're pretty sure we caught the true mean with this interval. So what do confidence intervals look like? So here's what they look like, actually. They look like this, but you sort of need to specify a little bit more. So let's here's what I mean by that. Let me show you. So let's take a look at our confidence interval again. We know we can go calculate a true. We know that the mu of x bar should be 633.37. And if we have this number over here, we had a 643, which would be over here somewhere. What we can say is, hey, that's our x bar. If I add the margin of error to it, so this would be the plus margin of error side, and I subtract the margin of error from it, what I end up with is an interval. And that interval here, if you look at it, if we trace it back up to the original distribution, what you'll notice is this interval, the way I've drawn it, catches the true mean. Okay? So depending on how sure I want to be about catching the true mean, is it determines the confidence level of our confidence interval. So let's pretend I say the following. I want to be 95% confident that we catch mu of x bar, or mu of x, which is theoretically they're supposed to be the same. So that's what we're asking for. We want to be that confident. Here's how you build a confidence interval. Confidence intervals look like this: x bar plus or minus. Now the margin of error, what we do is we use a z-score, and we can do that because we can make sense of it in this case because we know our distribution of sample means is going to be normal, multiplied by the standard deviation of x over the rad of n. Now, z star is based on the level of confidence you want. So there are charts and so forth. But if we want to be 95% confident that we've caught the true mean, what we're saying is we want to catch the middle 95% of area under the normal curve. Then you can look up in a z chart and find that negative 1.96 to positive 1.96 as a z-score would do that. So if we want to do a 95% confidence interval, then we're going to use z star equals 1.96. That's what we're going to do. So here's what our confidence interval would look like for the specific x bar of 643. What we would have is our 95% CI would equal 643 plus or minus 1.96 times 94.89 over the square root of 30, because that was our sample size. More specifically, we'd end up with 643 plus or minus 1.96 times 17.32. And why don't we go use our calculator and figure that out. So we'll do second quit. 643 plus 1.96 times 17.32 equals 676.95. So our confidence interval is starting to be built here. We have our upper limit of 676.95. And then we'll get our lower limit in a minute. Here we go. We do second enter. We're going to change that plus over here. We'll get over there. Slow calculator. Sorry about that. To a minus. And hit enter. And we get 609.05. And there you go. This is your 95% confidence interval for the particular x bar that's equal to 643. So what we say is we're 95% confident that we've caught the true mean with this interval. Now in this particular example, we actually know that the true mean, mu of x, is 633.37. And sure enough, that's in this interval. And so this interval caught the true mean. Now, if we go back to this picture, you'll notice we got other x bars. So every time there's a new x bar, like here was the 643, we did a confidence interval for that. I'm putting a check mark next to it because the confidence interval there caught the true mean. We could do a confidence interval for this one also. So let's go do that one, see what happens. So x bar plus or minus z star sigma over rad n. And if we're going to stick with 95% confidence interval, which we will for now, then z is 1.96. This is 94.89 divided by the square root of 30 and plus or minus. And this time we're using an x bar of 627. So 627. Okay, so now we'll go back to our calculator and figure out this new confidence interval. So here we go. I'll do second enter, and I will change this to 627. Oops, hold on a second there. Somehow I didn't press the 6 hard enough. 627. Here we go. We hit enter, and we get 593.05. So that's our lower bound, 593.05. And then we'll get the upper bounds. I'll go back to the calculator. I'll do second enter, and I'm going to go change that minus to a plus. We hit enter, and we get 660.94. 660.94. Okay, so this interval also catches the true mean. I'm not really surprised by that because if I look at the picture, this x bar was pretty close to 633, so I'm not surprised. So here's another check mark. This one also caught the true mean. Let's do an x bar, one more constant interval to 609 and see what happens. So here we go. So it's going to be 609, and by now you realize it's going to be plus or minus z star times 17.32. And this is still a 95% constant interval, and we know that because we're using 1.96. All right, so lastly, here we go. Let's do this. Second enter. And here we go. We'll change that 627 to a 609. We hit enter, and we get an upper bound of 642. 642 point something. All right, and then we'll get a lower bound if we do go back to our calculator. And we do second enter. Here we go. All right, here we go. Minus, and we get 575. All right, this one also caught the 633, the true mean. Now, I shouldn't be surprised by this because if I'm doing a 95% confidence interval, then what that's saying is that in 95% of all possible samples, the true mean would be caught. So you have to remember, if we go back to this original distribution, there's lots of different x bars I can calculate. And the 95% confidence interval is saying, hey, look, the margin of error is big enough that this number that I'm adding and subtracting from my x bars is big enough to catch the true mean at 95% of all confidence intervals. Okay. Well, keep in mind, it's possible maybe you were extraordinarily unlucky and you get an x bar that's really low. Maybe you got an x bar down here, x bar 4, of 570. Well, if I find the confidence interval for that, I'm going to have 570 plus or minus 1.96 times 17.32. And if I just do the following, if I just change this to 570 and plus, okay, I get an upper bound of my interval of 603. So don't even worry about the lower bound. The upper bound is 603. And this is some lower bound over here. It's going to be lower than 603. So you'll notice that this interval does not catch 633. And again, this is going to happen from time to time because if we get an x bar that's far enough away, the margin of error is not big enough to reach over and catch. The margin of error on this only reaches over to here, about 605. Actually, that's not the scale. You can see that. Sorry about that. We'll probably only reach over to about here, 605. It's not reaching over far enough to the left to catch the true mean. So that's what confidence intervals do, is they form a net around your x bar, and you hope that that net is going to catch the true mean. If it's a 95% confidence interval, then what we can say is in 95% of all possible samples created in this way, those 95% of all those samples would catch the true mean of the population.